And then people, it's like many people are afraid of science, but they don't realize they're interested in it. When you talk about warp drive or time machines, they suddenly get interested, and they don't realize it's kind of forefront science.
Yeah. Tim Maudlin was saying that his favorite parts of most physics courses, most science courses in general, are the first lectures because they're selling you on the course. So he's like, when I went to quantum field theory, they told me about this is the most impactful theory in science. And then lecture 3 is on Green's functions. He's like, well, what happened to studying what is? And when you ask what is, they're like, oh, that's philosophy, actually. Don't even ask that here.
Yeah, well, I mean, there's a lot. Well, quantum field theory has certainly always been, and probably, well, I don't know if it remains, but it's always been the most challenging class to teach in graduate school or to take. And there's just a lot of stuff and a lot of intellectual baggage that you need to do. And you can't, and before you can, philosophy is useful for framing initial questions of the world, but physics has long gone beyond those initial questions, so that it's driven by questions that are often quite mathematical in nature. And people don't realize that you can't just sort of start with those questions and expect to reach anything without going through the remarkable baggage that's been developed, and that has taken you far away from the questions. So, what is a fancy question, but it actually, as I talked about in Universe or Nothing, that the whole concept of something and nothing has changed dramatically because of physics, and people don't like that, but I don't care. It's the way it is. It's called learning, and we now realize that, as a matter of fact, because of quantum field theory, that the difference between something and nothing is not so great as imagined before, because nothing has lots of something in it.
Yeah. Let's speak about that for a moment. When I was younger, I remember questioning the universe, and I couldn't figure out how anything could come from nothing. And that was something that I had asked my brother, who was studying physics at the time. And then he mentioned quantum fluctuations, and I was 8 or so. And then it was approximately at that point that I became an arrogant and inexorable atheist.
Wow. Your brother did God's work, as we say. Go
on. I realized years later that's not an explanation to say vacuum fluctuation.
Sure. Yeah.
But I didn't know that at the time. So because I didn't know, I thought that was an explanation. However, you have now figured out some way of making that indeed an explanation. So can you cover that, please?
How you get something from nothing, you mean?
How the universe can come about from vacuum fluctuation.
Yeah, well, I can give you a summary. As I say, I wrote a whole book about it, so it's kind of, but look, the key aspect of quantum mechanics, which I do talk about in the new book, is that the quantum universe is many things are happening at the same time, and in particular, quantum fluctuations are happening all the time. We can't see them, but quantum systems are constantly fluctuating, and when you combine quantum mechanics and relativity, it's even more exciting, because it says that empty space isn't empty. So the key thing about quantum mechanics, when you combine it with relativity, and I've described this in a number of my books, it implies that empty space isn't empty. It has no real particles, but over time scales that are so short that you can't measure them directly, and this is the uncertainty principle of quantum mechanics, things can happen that you can't see. And in particular, particles can pop into existence that weren't there before, and then pop out of existence in a time scale so short that you can't even see them. Those are called virtual particles. It may sound like counting angels on the head of a pin if you say, well, these particles are there, but you can't see them. Well, we can't see them directly, but what we can do is see their effects indirectly. We know they're there because we have an impact on the atomic energy levels of atoms. They allow us to calculate the atomic energy levels of atoms with an accuracy that's unprecedented in all of science. So we know we have to include the fact that on small scales and small times, particles are popping in and out of existence. It's quantum fluctuations in quantum fields. That's why quantum field theory is relevant. Allow you to produce particles that appear and then disappear. Fine. Well, that's for normal quantum field theory with particles and in space and time. But gravity is a theory of space and time. And so if gravity is a quantum theory, and that's a big if, we don't know for certain, but we have no reason to suspect it isn't, then the variables of that theory, space and time, become quantum mechanical variables. And then space and time can fluctuate. And you can start literally with no space, no time, and then have a little universe with space and time appear and then disappear. Virtual universes can pop in and out of existence.
Mhm.
And in quantum gravity, that kind of phenomena happens. But it can happen that if a virtual universe pops into existence with zero total energy, then the laws of quantum mechanics and relativity say that virtual universe, in fact, can be real. It can exist for an arbitrarily long time, and then in order for it to not collapse again, if it say starts expanding and not collapses, certain processes have to happen. But if you asked, what would a universe that was almost 14 billion years old, that spontaneously arose from nothing by quantum mechanical processes, what would it look like today? And the answer is it would look just like the universe we live in. All the properties would be the properties of the universe we live in. Now, that doesn't prove that happened.
Yeah.
But it's strongly suggestive that possibility could explain the existence of our universe. Now, it's all possibilities right now because we don't have a quantum theory of gravity. I said if space and time, if gravity is a quantum theory, and it's a big if. We don't have a theory of quantum gravity. We may, string theory is a good candidate for that, but no one knows if it is a theory of quantum gravity in our universe. And so that's an open question at the forefront of physics, one of the known unknowns, if you wish.
And what's the name of that theory? What you just outlined, which is, okay, look, if you have fluctuating quantum fields and you were to combine general relativity, you have fluctuating space-time itself, universes can... It's just a proposal, a vague proposal, or is there a name attached to it?
No, there's no names attached to it. I propose it. Other people have proposed it, but it's just a consequence, if you wish, of having a quantum theory of gravity. And lots of people have thought about it, Hawking and Hartle, and Stephen Hawking has obviously thought about it a lot. I have, other people have. But it's right now a plausible idea, but it's not yet a complete theory because we do not have a full theory of quantum gravity.
If you enjoyed this TOE clipping, then the full video is linked in the description. You should also sign up for TOE Mail, which is again in the description and the pinned comment. You'll receive immediate access to all exclusive updates from the Theories of Everything podcast. It also helps me communicate directly with the core TOE community. You'll also receive my top 10 TOEs. Think of it as the intellectual version of Quentin Tarantino's Obsession.